All right, welcome back. So let's talk about detection with either unequal costs, many hypotheses, or vectors of observations, or maybe all of these things together. So maybe a combination of all of these different features. And the point of this video is to give you a framework to take the ideas that we've learned in detection theory, where we started with some kind of simple binary hypothesis and some examples. We took that to the likelihood ratio. And now we kind of want to show you how can you use this framework in pretty complex scenarios. So you might get a lot of different observations which are modeled by some sophisticated conditional probability models, or maybe you have many different hypotheses representing different possibilities in some application, and you still want to use this framework. So we're not going to do a lot of examples here, but we're just going to show you how this branches out to get to its full sophistication, since you've already learned all the basics you need to know. All right, so let's just think about why we might need some of these generalizations. Okay, so these are very natural generalizations, and they're building off what we started with binary hypothesis testing. Okay, so first of all, we've mentioned this before, but what if the cost of missing the detection, so misdetection, what if that's not the same as the cost of a false alarm? And it's very easy to imagine scenarios where that's the case. Okay, so as an example, let's say I do a quick X-ray test for cancer. Okay, and what's the false alarm cost? Well, what if it's just a follow-up scan? Not too bad. What's the misdetection cost? Well, maybe there's an undiagnosed malignant tumor. Okay, so I basically send someone away. I say, you're probably fine, but I miss the tumor, and bad things can happen from there. So maybe I want to put more emphasis on detection in this case. All right, well, what if there are more than two hypotheses? When can that occur? Well, there are a lot of different scenarios. I'm just going to give you one here. So let's think about high-rate wireless communication. The way in which we send multiple bits, so we want to send a very high data rate, we need to send many bits in a single waveform. So the way to do that is to have many different choices of waveforms and to have each bit sequence corresponding to a hypothesis. So just to give you an example, let's say I have 8 different signals that I could send. So there are 8 choices, so that means 3 bits, because 2 to the 3 is 8. And then my job is to decide which of these 8 waveforms I decided, and then output the corresponding 3 bits. And finally, let's say I can observe a lot of different random variables, and that can happen in many cases. It could have happened in the, this X-ray test we had in wireless communication, but let's think about yet another scenario here. And vectors are really just for convenience of notation. So you just have multiple observations. Let's say I want to decide whether or not to engage the anti-lock brakes on my car, and I've been collecting a lot of sensor readings from all over the car, including my velocity and what the, maybe I have some more sophisticated sensors these days, but I want to combine all that information and just decide whether to engage the anti-lock brakes or not. All right, well, let's start with this first case. Let's try to put some costs to false alarm and misdetection. So let's say I have 2 hypotheses. We could have more, but we're starting with this generalization. So let's say I have 2 hypotheses. We'll call them H0 and H1, and they have the usual conditional probability models. Okay, so in the discrete case, it's P of y given H0 and P of y given H1, or in the continuous case, F of y given H0 and F of y given H1. So the cost, Cij, of deciding I when actually j is true is the thing that we need. So in this case, C10 is the cost of false alarm, because I decide 1 when 0 occurred. C01 is the cost of misdetection. Now, I also have costs of C00 and C11. Those are the costs of correct decision, and we could set those to some values. We're just going to set them to 0 here. It doesn't really matter. It just depends whether you want to factor those in or not. We're just going to say that correct decisions are the same, but you could rebuild this from scratch if you wanted, also putting some values to those. Okay, so for a decision rule with some decision regions, as we had before, so let's say I have A0, the y values where I decide 0, and A1, the y values where I decide 1, now what I'm going to care about is the expected risk, E of R. So the expectation of this risk random variable R. And this is a notation that shows up in statistics, but basically risk is just meaning the same thing here as cost. So it's basically saying what's the average cost, but people tend to call it expected risk. So here, the discrete case is going to be that the expected risk is the sum of this cost, C01, times the probability of y given h1 times the probability of h1 plus the sum over a1 cost of 1, 0, probability of y given h0, y times probability of h0. So let's just unpack that. Basically what it's saying is in the decision region for a0, then the costs I'm worrying about are misdetection because I'm deciding 0 when 1 occurred. And in the decision region a1, I'm worried about false alarm because I'm deciding 1 when 0 occurred. So I'm worried about the cost C10. In the continuous case, I'm going to get exactly the same thing. I'm just replacing all the sums with integrals. Okay, so here are the integrals that are just the same thing that we had above. And I integrate over the regions A0 and A1. So this term on the left is the misdetection cost, and this term on the right is the false alarm cost. Okay, so how do I do this optimally? Well, it turns out the minimum Bayes risk decision rule is the way to do that. Okay, and all it's going to do is just pick a particular threshold for the likelihood ratio. So I'm going to pick the threshold C10 P of H0 over C01 P of H1. Okay, so when the likelihood ratio is larger than or equal to that value, I'll decide 1. And when it's less than that value, I'm going to decide 0. Okay, and remember the likelihood ratio, we saw that in the previous video, that's the probability of y given h1 over the probability of y given h0 in the discrete case. And in the continuous case, it's the same thing, but just with conditional densities. All right, so just to remind you of that. So why is this the right thing to do? Well, what it does is it tries to avoid mistakes that would contribute more to the expected risk. So if I make a mistake towards misdetection, and that's more costly in this case, given its probability, so weighted by the probability, then I avoid the misdetection. All right. It turns out that this is really just some particular point on the ROC curve, and we just have a motivation for picking that point because we're motivated by these costs that we believe are accurate. So we believe that for our scenario, these are the right way to attribute costs to misdetection and false alarm. So we pick a particular point on the ROC curve. We'll just do one example just to kind of see how this works, but you could get into a lot more depth. All right, so let's just write out some conditional PMF values. So probability of y given h0, we'll say for, and probability of y given h1. So we'll say for y equals 0, it's 1/10, then 3/10, then 2/10, and then 4/10. And we'll say for the other one, it's 5/10, 3/10, 1/10, and 1/10. And so the likelihood ratio is 5, 1, a half, and a fourth. Okay? So that's just probability of y given h1 divided by probability of y given h0. Let's come up with the probability of hypothesis. We'll just say that probability of h0 is 2/3, probability of h1 is 1/3. Okay? So h0 is more likely than h1, but we'll say that misdetection is 4 times as costly as false alarm. Okay, so what we're going to see here then is that this threshold is actually going to be at 1 times 2/3 over 4 times 1/3, and that's going to work out to be 1/2. Okay, so it's tilting things towards avoiding misdetections because the cost of misdetections is 4 times higher, even though they're half as likely to occur because the probability of that hypothesis is lower. Okay, so basically I'm looking for the values where the likelihood ratio is greater than or equal to 1/2. I get these values. So the the region where I decide 1 is 0, 1, and 2, and 0 is just where y equals 3. To get the expected risk, I'm just going to write out that formula I had before. So I sum up over A0 the misdetection cost, and I sum up over A1 the false alarm cost. All right. So in this case, A0 is just 1 point. So I'm just going to have the misdetection cost 4 times 1/10 times 1/3, plus I have 3 points in A1, so I have 1/10 plus 3/10 plus 2/10 times 2/3. So if you add all of that up, you get 16 over 30, and then you get 8 over 15. So that's just a simple example just to show you how this minimum Bayes risk detection works. So all I'm doing is just picking a particular threshold. Turns out this is the optimal way to do it if what I'm trying to do is minimize expected risk or average costs, and I know that these are the right costs to assign. All right, what's next? Well, let's have M hypotheses, not just 2 hypotheses, we're going to have M hypotheses. Same, basically everything's going to hold up, we just need a little bit more notation. So I need M hypotheses, we'll call them H0 up to HM minus 1, but you could call them whatever you like. This is just the standard notation. These are events that partition the sample space. So now we don't just have 2, we have M. All right, I'm going to get a measurement. Again, let's just say it's a scalar, so it's a measurement or it's an observation. And we're just going to say this is a single random variable y that I get. And as usual, it's going to have some conditional distribution, right, for each hypothesis. So in the discrete case, I'm going to have the conditional PMF of y given hi. If hi occurs for I equals 0 up to m minus 1. Continuous case, same thing, I have f of y given hi. All right, we're going to have a detector or a decision rule. And what that's going to do is it's going to take in y, and it's going to output a decision. We're going to call it u. We don't really use that anywhere else, but just to call it something. It's going to output a decision which is 0, 1 up to m minus 1. And it's going to do that to decide that hi is the thing it thinks occurred. And this is going to partition the range of y into m decision regions, which we're going to call ai. So ai is the region where I'm deciding I, and I have to do that for all m hypotheses. The probability of error, PE, that's just the sum of these probabilities that I go into the wrong region when hi occurs, weighted by the probability of hi. Okay, so remember before, the wrong region was A0 if I had H1, or A1 when I had H0. But here, because I have M hypotheses, any one of the other decision regions is wrong. So if I have H0, then decision regions 1 up to M minus 1 are all wrong. So the probability of error under H0 is when I go into any of those other regions. So I don't belong to my own decision region. So the only thing that really happens here is this event can just become a little bit more annoying to calculate. All right, we need a bit more notation. So our notation here, remember, if I have max over some x in A of some function g of x, that's going to return the largest value of g of x for x in this set A. The notation that we're going to introduce is this thing called argmax of x over A of g of x. That returns the argument of x in this set A that attains the maximum value of g of x, right? So before, what we were doing is looking for the maximum value of the function. This argmax tells me the x that hits that maximum value of the function. Okay, we'll see some examples of this in a second, but in this class, we're going to arbitrarily break ties in favor of larger values of x. That doesn't matter so much, it's just we have to break ties in some way. This is just the way that we're going to do it. You can pick your own way if you like. And by the way, we're not going to write this out explicitly, but you can define the min and the argmin in exactly the same way, except now you're looking for the smallest value and the argument that achieves the smallest value. So now, with this notation, the maximum likelihood, or ML rule, in the discrete case is just going to be very simple to write out. It's just d of ML is the argmax of I of P of y given hi, plugging in y. So basically, I run over all of these conditional PMFs, and I choose the I, which selects the highest value here once I've plugged in y. That's what we were doing before. We were comparing probability of y given h1 to probability of y given h0, and picking 1 when probability of y given h1 was larger. Here I have m things. It's really annoying to write out all of those different comparisons. So all I do is I write argmax to tell you, pick the one that's the largest. Same thing in the continuous case, pick the hypothesis for which P of y given that hypothesis is the largest. The map rule, again, we can use this notation and get the same thing. Nice thing about the map rule is it's optimal. As before, you need to know the hypothesis probabilities. Maybe you can get those, maybe you can't. But let's say you have them, you can do this. You take the argmax of the conditional PMF times the probability of the hypothesis. Pick the largest one. That's the hypothesis you're going to have for the map rule. The continuous case, same thing. Just use a conditional PDF instead of the conditional PMF. Okay. And remember, you need to know the hypothesis probability. That's it. Okay. What's an example of this? Well, let's generalize what we saw in the previous video where we worked with the Gaussian. So what we're going to do is we're going to say that, let's say under HI, we're going to have y, which is Gaussian, and it's going to have some arbitrary mean mu I and variance sigma squared. And I is going to go from 0 up to m-1. And these mean values can be anything that you like. That means that the conditional PDF of y given hi is going to be 1 over root 2 pi sigma squared. That's just this normalization constant. We're not going to worry too much about that. E minus y minus mu of I, the mean, squared, over 2 sigma squared. Okay, so what we're going to do here is we're just going to assume that the hypotheses are equally likely, and so the map and ML rules are going to be the same. We're not even going to worry about working out the map rule, so we're just going to work out the ML rule. So let's just say that the hypotheses are equally likely. Okay, and so what's the ML rule going to be? We're going to use this notation that we developed and just see how to manipulate it a little bit. So what we're going to get is argmax of the conditional PDF, and we're going to run over all the choices of hypotheses and pick the hypothesis that gives us the largest value of this conditional PDF. So the first thing I'm going to do is I'm going to just plug in for this conditional PDF, which I've written out above. So I'm just going to rewrite it here, keeping this argmax notation around. Okay, so here it is. So I have my normalization constant and my exponent and all that. Okay, for the next step, what I'm going to do is I'm going to drop quite a few terms. So I'm keeping this argmax, and I'm going to drop the normalization constant. I'm actually also going to drop out of this e to the minus something. I'm just going to have minus the square of y minus mu I squared. Why can I do this? Because both of these expressions are going to be maximized by the same value of I. Okay? So the same choice of I is going to be maximizing both of these expressions. Okay, so it doesn't matter whether I have this normalization constant, right? So I can throw that out because I don't care about the value of the max. I just care about the hypothesis that attains that value, right? So I can throw those out. And so similarly, if I have e to the something, then that something, if I make that large, then that makes the e to the something large. So I can throw that out too. So you have to kind of think about that for a little bit, but this is totally valid. The next thing I'm going to do is get rid of this minus sign. And the way I can get rid of the minus sign is by switching the max to a min, right? Because argmax of minus g of y is equal to argmin of g of y. Because to make the negative of something large is equivalent to making the minimum of that something, or finding the minimum of that something. And again, because I don't care about the value, I just care about the argument that attains the value, it's fine for me to do this. Okay, and so now just kind of continuing onwards. So now I have this argument again. I'm going to drop the square, and I'm just going to have an absolute value. And that doesn't matter too much. It's just cleaner to write it this way. And again, the reason I can do this is both of these expressions are going to be minimized in this case by the same choice of I, right? So what I'm trying to do is pick the mu I that is closest to y. That's going to give me the smallest value, right? So I'm going to choose the hypothesis that gives me the mu I that's the closest to y, right? And that makes sense because that's going to result in the highest value of this likelihood. Okay, so I'm trying to do that. And it doesn't matter whether I'm plugging that into y minus mu I squared or the absolute value of y minus mu I. In both of those cases, the same choice of mu I is going to give me the smaller value. So in terms of finding the argument, I can just throw out the square and just be left with the absolute value. All right. And as I mentioned before, so what's the map rule in this setting? we're not going to work out the probability of error. You can do it, but it's actually a little bit tedious. But the thing here is that since the hypotheses are equally likely, then the probability of the hypothesis doesn't play any role in my decision. So the map rule and the ML rule are going to be exactly the same. Okay. Our third generalization. That's going to be when I have many observations. So we're going to have a vector of observations. Let's just stick with this general setting. So let's actually say we have M hypotheses. Okay, so I'm going to have H0, H1 up to Hm minus 1. And I'm going to have the measurement or observation, which consists of n random variables. Okay, and they're going to be Y1 up to Yn. And we're going to collect those into some random vector y underscore, right? So that's our notation for a random vector. Okay, so remember that that's just this vector, y1 up to yn. Okay, in the discrete case then, our probability model is p of y vector given hi, if hi occurs, and in the continuous case is f of y vector given hi, if hi occurs. Okay, so this is just our framework. So our detector or decision rule is going to take this y vector and it's going to output a decision, which is one of the M hypotheses. Okay, and what that means is just deciding that it thinks hi occurred. And so that's going to partition the range of this vector now, not a scalar, but a vector, into some decision regions, right? So whatever its range is gets partitioned into each respective choice. And the probability of error, as before, is just going to be the sum of the decision. So basically, I'm going to make a mistake if my vector does not belong to my decision region, even though this hypothesis occurred. So if hi occurs, but I fall outside of ai, that's a mistake. The only problem is this can become very difficult to compute. So when I get into some higher dimensional spaces, even something as simple as a Gaussian with different means, these can become quite difficult to compute. And you usually have to turn to some approximations or bounds or other tricks to even start to get a handle on them. But that's kind of beyond our scope. What we're going to do is just write out the ML and map rule. This is actually going to be pretty simple. All we're going to do is just use our nice argmax notation. So DML going to be argmax of I going up from 0 up to m minus 1. Again, plugging in my vector into this conditional PMF. Continuous case is going to be the same thing. Plug into the conditional PDF, choose the largest value. Map rule, again, we're going to use this notation. We're going to get a really compact formula. It's going to be the best possible thing I can do, assuming I know the hypothesis probabilities. So the map rule is going to be the argmax of the conditional PMF of y vector given hi times the probability of hi. I'm just going to choose the largest among those values and pick the corresponding hypothesis. And so in the continuous case, I'm going to do the same thing. I'm going to choose the largest among f of y vector given hi, y bar. Okay, so basically I just choose, again, the weighted conditional PDF. So the problem here is we can write all these rules down pretty compactly now using this argmax notation. But what can start to happen if I get into larger and larger problems is that these might not actually be efficiently implementable. Okay, so here's an example. Let's say I have 100, L is equal to 100, and I have 2 to the L possibilities. When could that happen? Well, it's very easy. Let's say I have a packet corresponding to 100 bits. That's not that many bits. We send more than that bits all the time. You've received many, many, many more bits than that just to watch this video. And the wireless receiver in your device had to make decisions about many, many more than that number of possibilities. But if you try to plug in to this thing and find the largest possibility among 2 to the 100, that's an enormously large number, and that search done in brute force just can't be done. Okay, so what can happen here is you might actually run into a computational barrier, right? So the trick here in detection theory is to find a computationally efficient procedure that can come close to the performance of the map rule or even the ML rule. So that's actually becomes the trick, is that once you have a big vector of observations and many, many hypotheses, how can you actually start to evaluate this at all? Okay, so that's where you can run into trouble. Again, kind of beyond our scope, but there's a lot of interesting stuff to study there and think about. We're just going to work out a simple enough example just to get a geometric sense. Okay, so our example is going to go back to this Gaussian case, but we're going to stay in 2 dimensions now, not 1 dimension. So I'm going to observe a vector. So under H0, my vector is going to have mean vector mu0 and covariance matrix sigma of y. And under H1, it's also going to be Gaussian, and all I'm going to do is change its mean vector to mu1 vector. Okay, so what are these vectors? Again, I'm going to give you them to you specifically. Mu0 vector is -1, -1, and mu1 vector is going to be +1, +1. And again, I'm going to pick a very simple covariance matrix. We're just trying to keep this as simple as possible. It's going to be the identity matrix 1, 0, 0, 1 in 2 dimensions. It's going to have this determinant. It's going to be the diagonal 1 times 1 minus the off diagonal 0 times 0, which is going to be 1. And its inverse is also the identity matrix. So things here are really nice and simple, which is great. So I get the conditional PDF of this y vector under H0 is 1 over this normalization. So this whole normalization constant, it turns out to be 2 pi to the n determinant of sigma y, square root of that. And then the important thing is e to the minus 1/2 y vector minus mu 0 vector. And then sigma inverse times y minus mu vector of 0. And so that all simplifies down. If you multiply everything out, I get inside the exponent y1 plus 1 squared plus y2 plus 1 squared. Because the means here were -1, so I had -1 and just turned into +1, right? And this inverse of the covariance matrix was just the identity matrix, so I really just got the inner product squared here. Okay, so I can repeat the same thing for h of y vector given h1. And so I'm going to get 2 pi to the n, and that's going to be the determinant of sigma y. And it's going to be e to the minus 1/2 y vector minus mu1 vector transpose times sigma inverse times y vector minus mu1 vector. And then this whole thing is going to end up being exactly as what we have above. It's going to be 1 over 2 pi e to the minus 1/2 y1 now minus its mean 1 squared plus y2 minus its mean, which is just 1 squared. Okay, so what we're trying to do is decide when is the hypothesis 1 giving me a higher likelihood than the hypothesis 0. That will happen when y1 minus 1 squared plus y2 minus 1 squared is less than or equal to y1 plus 1 squared plus y2 plus 1 squared. Why less instead of more? Well, because I have e to the minus something, and so I need a smaller value to make that larger. That's why. I'm just going to expand both sides of this inequality and cross out terms. So I get y1 squared minus 2y1 plus 1, y2 squared minus 2y2 plus 1, comparing that to y1 squared plus 2y1 plus 1 plus y2 squared plus 2y2 plus 1. So cross out a lot of terms, cross out the y1 squareds, the y2 squareds, the 1s, lots of 1s. All those are crossed out. So what I'm comparing in the end is 0 to 4y1 plus 4y2. And so the ML rule in this case is going to correspond to something actually quite simple. It's just going to pick 1 when y1 plus y2 is greater than or equal to 0, and 0 when y1 plus y2 is less than 0. Let's think about that mathematically for a second. So what I'm doing is I'm just basically averaging my two coordinates, y1 and y2. And that makes sense because I'm basically seeing the same mean repeated twice, either -1 or -1, or +1 and +1. So I'm getting 2 looks at this mean in Gaussian noise. So it makes sense to average them. So that's great. What does this look like geometrically? That's also going to make sense. I'm going to draw this 2D plot. Okay, so I'm going to have this coordinate system for y1 and y2, my observations. I'm going to have mu0, which is minus minus, and mu1, which is plus plus. And if you look at this line, this y1 plus y2 equals 0 line. On one side of this line, I'm deciding for h0. That's when this is larger than 0. And on the other side of this line, I'm deciding for h1. So basically, these red arrows are showing me where I'm deciding h1, and these blue arrows are showing me where I'm deciding h0. And that again makes sense. I'm deciding for the closer mean vector, right? So it's very geometric in this case because of the Gaussian noise. I'm just trying to figure out which of those mean vectors is closer to my observation, right? So wherever I land, if I land on the top right of this purple line, I'm closer to the red point. If I land on the bottom left, I'm closer to the blue point, and then I just make that corresponding decision. So the geometry also works out really nicely. And these kind of simple examples help you build up some geometric intuition, which can help you reason in higher and higher dimensions. All right.